In in this video, we're going to continue reactions of alkynes. We're going to talk about how do we do reduction of alkynes. Reduction of usually means adding hydrogens to alkynes. Similarly, we have learned similar type of reactions of alkenes. Basically turn double bonds or triple bonds into single bonds by adding hydrogens to it. So we all know that double bonds or triple bonds are usually so-called unsaturated hydrocarbons because they're missing hydrogens. Every one additional bonds to the single bond will be 2 hydrogens less. So in other words, with a triple bond or alkyne, there are missing 4 hydrogens here. So potentially we can add 2 more hydrogens on each carbons. Now, there are multiple ways of adding hydrogens to triple bonds. We're going to talk about 3 of them here in this video. The first one is actually the same thing we've seen in the alkene reduction, which is using palladium carbon as the catalyst with hydrogen gas. So this kind of reduction will basically add hydrogens to the alkyne or triple bond carbons until it's completely saturated with sigma bonds. You basically can see this as hydrogens adding to the alkyne triple bonds to form a double bond first, and then we'll continue adding hydrogens to the double bond, eventually reach to sigma bonds. The other catalyst here using is so-called the Lindlar's catalyst. The mechanism is not required here, but the products here has to be remembered, which is going to be cis alkenes. So there are 2 things you can distinguish between the Lindlar's catalyst and the palladium carbon catalyst. One is that Lindlar's catalyst does not go all the way to a single bond. It only adds 2 hydrogens to the alkynes or the triple bond. The second thing is that the Lindlar's catalyst only result into cis conformation of the alkene, not trans. They will never achieve trans alkenes. So here's the mechanism of the the Lindlar's catalyst, which is very similar to palladium carbon one. You basically have a solid-based catalyst with the hydrogen atoms attached to it, and then hydrogen atoms will be added towards the triple bonds at the same time, and that's the result of the cis alkene product. So basically hydrogens are only added to the triple bonds from the same side at the same time. But we don't really talk about why it stopped at double bonds. We basically have just to remember this. So those are 2 catalysts we just talked about. Palladium carbon, that's one. It goes all the way to single bond. Lindlar's catalyst gives you a cis alkene product. Depends on what product you want. You can choose different catalysts here. The third one is a little bit different. It's called the sodium lithium ammonia reaction with hydrogens, of course. Now, this particular one is comparable to Lindlar's catalyst, whereas Lindlar's catalyst give you additional products of cis, but this reaction gives you specifically trans product alkene. It doesn't go to sigma bonds completely. It doesn't add 4 hydrogens. You only add 2 hydrogens, and it specifically gives trans product. Even though the mechanism is not required, but it's might be easier for you to look at the mechanism so you understand why it's actually a trans product. So basically, instead of like the addition of Lindlar's catalyst, both hydrogen atoms are added to the alkene triple bonds at the same time from the same side. This addition happens with 1 hydrogen first, and then the second hydrogen from the other side. And that's why 2 hydrogens were added in the tandem fashion, one first, the other one second, result into a trans addition or trans double bond product. Now, to summarize what we did, Palladium carbon catalyst gives you complete addition product, which gives you single bonds, which is there's no difference between cis and trans. Linder's catalyst and sodium, lithium, liquid ammonia gives you alkene products, whereas Linder's gives you cis alkene product, and sodium, lithium, ammonium gives you trans product. Let's take a look at a few examples here. Now you can pause the video here, see if you can draw the product out. Only the product, not the reaction mechanism for each one of these reactions. So the first one is the R triple bond with addition of hydrogens. The first one is palladium carbon catalyst. So we know that the first one is going to result into complete saturated alkanes. Now the important thing here is make sure you count the correct number of atoms so you can draw the product structure correctly. So in this compound, in the reactants, we can see there are 1, 2, 3, 4, 5, 6. Now when you number these carbons, since you are not trying to do the nomenclature, you can number them any way you want. Just make sure you have the same number of carbons on the product side. So we're basically looking for a carbon chain with 6 carbons with no double bond or triple bond here. So you can draw it 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. You can even number this in your mind quietly so you can ensure that there are enough carbons to be drawn here. It doesn't really matter if you draw it this way or if you draw it this way. These are the same thing. But of course you know that the triple bonds are used to be number 3 and number 4 here are gone because of the addition of the hydrogens. So in the reactant side, there are no hydrogens on number 3 carbon, no hydrogens on number 4 carbon. But now there are actually 2 hydrogens on number 3 carbon and 2 hydrogens on number 4 carbon. And those 4 hydrogens are actually from the addition of the hydrogen. Another way you can try to remember this is this actually goes through a double bond first and then goes to, with a 1 equivalent hydrogen you makes a double bond, with second equivalent hydrogen makes it a single, complete saturated single bond product. The second example is using Linder's catalyst, and also you can see the third one is using lithium ammonium. Now with Linder's and lithium ammonium, both reactions are going to give you double bond instead of single bond. So you only add 1 hydrogen gas or molecule to the triple bond. The same thing, we're going to try to make sure we are having the correct structure of the product. With 6 carbons on number 2, there's a methyl group. So let's draw the 6 carbon chain here. 2, 3, 4, 5, 6. It's never going to be a bad idea to confirm you have the correct number of carbons. And on number 2, there's another branch. And between number 3 and number 4, there's going to be a double bond. But you have to keep in mind, Linder's catalyst gives you cis product only. So we have to, if you just draw it like that, that will be wrong. But if I turn this into one, two, three, four, 5, you can have the other branch going this way or going this way. It makes no difference. So this gives you a cis alkene product. Now the hydrogen will add it to 1 on each carbon. And the third one will be similar to the Linder's catalyst, but it will result into a trans product. So with the triple bond where it is, there is a 5-membrane and 3-membrane on either side. So I'm going to just draw the 5-membrane. Now, with the triple bond, it's going to be linear geometry, but double bond will be bent over, but it's not going to be cis, it's going to be trans. So on the other side, you're going to have the triangle ring. So the cis product will never be correct for this reaction. The trans product is the only product in this reaction, with one hydrogen added to one of each carbon in this case.